Assalamu alaikum. Hello, everyone. We are still in the topic of linear regression. Just to recap, last time we explained gradient descent algorithm when we have a single input feature problem. So for the linear regression. So we talked about gradient descent and we explained how it works. It's an iterative algorithm where you start with an initial guess for the global optima for convex functions, and then you keep moving towards the negative direction of the gradient, and with that you will eventually be within the neighborhood of the for sufficiently small step size or learning rate, you will be within the neighborhood of the global optima. So why we are moving in the negative direction of the gradient? Because actually the gradient is a vector that points towards the maximum or the greatest increase or of the function. Okay, the direction where the function increases the most, or it's also called the steepest ascent. So if we are moving in the negative direction of that, so then we are moving in the direction of the steepest descent, or where the function decreases the most. So as we keep moving towards the negative direction of the gradient, eventually with very small step size, at least we will be with the neighborhood. We may not because the step size or the learning rate is not exactly zero. So then we will be at least with the neighborhood of the global optima for convex functions. And for in general, we will be with the neighborhood of a stationary point in general, because if the function is non-convex, then we may end up like within the neighborhood of a local optima, not the global optima. Okay, so that's gradient descent. Today we will start we will move to multiple, like when we have multiple input features. So multiple input, single output linear regression. So that we are just going to extend the idea of single input feature to multiple input features. So here our estimate of y is nothing but linear combination of the input features. Okay, so here we are appending a feature of all ones at the beginning to account for beta 0. So then we can write the sum this way. So what I mean by that, so this is y hat. This is the predicted value or the estimate for the actual y we are building from our model. So what I mean by we add the feature of all ones, let me show it to you here. Here. Okay, so here we concatenate all the model parameters to form this vector here. Starts with beta 0, okay? Beta 0, beta 1, all the way to beta n. And beta 0 is not multiplied with any of the input features. So that's why we add the feature of all ones here, okay? So for example, the estimate y for the first sample is beta 0 plus beta 1 x11, which is the first feature for the first sample, plus beta 2 x12, 2, and so on. So that would be, F here represents h in our case, okay? So the h of the ith sample, h of xi, is beta 0 plus beta 1 times the value of the first feature for the ith sample, plus beta 2 times the value of the second feature for the ith sample, and so on. So this is the matrix format of this problem. And in fact, if you remember our, let me go back here. Our loss function is defined as this, right? It's the sum of the square differences between the estimate value for the ith sample plus the actual one, right? So the sum of the square differences in the matrix and vector format can be written as this one. So it's the norm square of the difference between y hat. This is y hat, okay, x beta. So this is x is this matrix, x beta. So this is y hat, okay? So it's the norm square or norm 2 square of the difference between y hat and y, okay? So we can write it in this format, okay? So this exactly equivalent to that, okay? So then now, if we wanna, we can run the gradient descent using this function, or we also can actually use the matrix format, as we will see later on. If we wanna like treat every beta, every one separately, then So we're going to compute like every component in the gradient vector separately. So because every component in the gradient vector, the z component is the partial derivative of the cost function or the loss function with respect to the z beta. That's it. So that's like the gradient vector. It's a vector. It has like elements, and the z element is the partial derivative of our cost function with respect to the z beta. So if you take this, the derivative of this with respect to the z beta, it will be this. Okay, so 2 comes here times h of xi minus yi times xj of I. Okay, the value of the z feature for the ith sample. Because actually, if you think about it, and you'd sum over all of this, because if you think about it, come back here. So all these terms here, okay, only the z term here is a function of z beta. So the derivative of this with respect to beta 2 is equal to 0. The derivative of this with respect to beta 2 equal to 0. Beta 2 exists only here. Okay, so the derivative of this with respect to beta 2 is equal to this. Okay, x2 for the ith sample. And then you sum over all of these samples. So that's, yeah, it's a high school stuff. So I assume you know how to compute the derivative, right? So this is the derivative, okay, with respect to the z beta. Then if you want to update the z beta, so the new version of the z beta is equal to the old version minus the learning rate times the partial derivative of our cost function with respect to the z beta, as we did with beta 0 and beta 1 for the SISO problem, okay? Then the main the algorithm will be like this. We start with a random initialization for all the betas, and then as we update, okay, so this is how we do it. Okay, so we compute the gradient, the partial derivative of the cost function with respect to the z beta, and then we move according to this step. Okay, and we stop when the same criteria we have for the size, when the value or the new value of the function is greater than or equal to the old one. Okay, that is like if we want to do it separately. Okay, like if we want to update every beta separately, like not in a vector matrix format. For if we want to consider the matrix format, we can actually compute the this is the optimal solution that is computed by simply taking the derivative and equating to 0. So if we come here, so as I said, this is the function. If you take the derivative of this, let me show you here. If you compute the gradient, sorry. So here, this is the gradient, okay? So simply here, the 2 will come here, and we will have x beta minus y times the derivative of this with respect to beta, which is equal to x transpose, because x is a matrix. And that's what we get here. X transpose times x beta minus y is equal to 0. And this is a vector, okay? Because every one of these partial derivatives should be equal to 0 at the optimal point, or the minima for convex functions. So then just a simplification of this x transpose x beta is equal minus x transpose y is equal to 0. Then you take this here, it will become x transpose x beta is equal to x transpose y. Then we need to multiply with the inverse of x transpose x, so we get rid of x transpose x here. So then we end up having beta is equal to x transpose x inverse times x transpose y. That's the closed form solution. We can also run gradient descent, okay, with the matrix and vector format here, okay? So beta k plus 1. So as a vector, the whole beta together, all the betas, we're not updating every one separately. The whole vector, beta k plus 1, this is a vector, okay, is equal to beta k minus the learning rate at iteration k times the gradient of the cost function with respect to beta k, which is equal to this, right? When we computed it here, it's this. In general, it's equal to 0 at the minima. But in general, at any point, it's x transpose x beta k minus y, right? It's this one, x transpose x beta k minus x transpose y. So this is the gradient. So if you are at the, like at iteration k, you have beta k. So you plug it in here, you compute the gradient of your cost function with respect to beta k, and you plug it in here. So then you move, okay? So eta could be constant, and we could actually make it a function of the of the iteration. So as we are moving more towards the minima, we can make it smaller and smaller. That's why in general it can change. That's why we have eta k here, okay? Instead of it. Eta here represents is equivalent to lambda in our main slides here, okay? So then now let's do it with, okay, let's look at this data here, okay? So we have a number of features, okay? We have 8 features and this is the target variable y, okay? So the first thing we will do here is to look at the correlation, okay? Let me do the, okay, let me comment out this and look at the correlation matrix and the heat map. Let's look at the correlation here. So here, so we have the correlation between every feature and every other feature and every feature and the target variable y here, okay? So as you can see here, x1, there's a happen here, okay? Okay, x1, okay, and y, okay, there's a like correlation between x1 and y, okay? And again, so now you see there is a correlation, okay? But to make sure that this is, there's a like linear dependency, because as I said, the correlation may capture also the non-linear dependencies, okay? So now you want to build a model where you want to linearly relate y to the input features. It's good to not only look at the what the correlation is telling you isolated from the scatter plot. Look at the scatter plot as well. So there seems to be correlation here. So if you want to know, like in average, the relation can be approximated by a line, then look at the scatter plot to see if it's a linear relation in average, or it could be non-linear relation, because x1, like for example, yeah, anyways, so that's the idea. So always look at both the correlation matrix as well as the scatter plot to see the relations. For example, here, x1, let's take one that is weakly correlated. This one, x4, is weakly correlated to y. There's very weak correlation. So this you may drop, okay? Or before you drop, look at the scatter plot. Maybe y is not linearly related to x4, but maybe could be there could be some non-linear relationship. Then maybe you want to go beyond linear regression. You want to go to polynomial regression, okay? You want to consider like yeah, go beyond in general, go beyond linear regression. So it's good to look at these values, okay? So and also look at the scatter plot to come up with the final conclusion, okay? So because, for example, these two are very weakly correlated to y, you may drop these two, okay? If you less features is sometimes is beneficial for the learning, okay? Also, you look at another thing. You look like to the correlation between the features themselves. If there are two features that are very correlated to each other, then you plot the scatter plot. Okay, if it's like it's a linear relation, maybe you need to drop one of them. Okay, if it's a non-linear, maybe it's better you keep them, so you actually can come up with some like a polynomial regressor. Okay. Because if one of them is like a higher polynomial degree of the other one, then actually what you are doing is not linear regression with respect to at least one of the features, okay? So the bottom line, it's good to look at the correlation to decide if you want to drop some of the features, okay? You may drop the weakly correlated ones, okay, to the target variable, and also the features between the features themselves, okay? If they are two features that are very correlated. For example, if one of them, like if the extreme case, okay, if the correlation between two features is equal to 1, maybe you need to drop one of them, because it's just redundant information, just like like creating the problem of multi-collinearity, and that may confuse the learning of the model. So you just drop one of them and you are left off with the one that is enough, because the other one doesn't really tell you any new information. It's just redundancy, okay? So it's good to look at the correlation, okay? So for example, here you can also print like display what are the most correlated ones. You may consider only those, or another way is maybe you keep all of them, but we're not going to consider the OLS, the ordinary least square. So we're going to actually consider like the penalized or the regularized linear regression, because this is, we're going to come to that later. This is actually a way where actually by introducing the regularizer, you're not manually dropping, like removing some of the features. This will happen as a result of minimizing this function. So with that, we may like push the weights of some features to be very low or even small for some of them. Okay, you're killing like any redundancy or any weakly correlated features to the what you are trying to predict. So you can actually at this point here you can you can build one model where you manually remove the weakly correlated ones to the target variable, as well as you, if you have many that are very correlated to each other, you may remove some of them, and you build model based on that, and you see like test the generalizability of that model in your testing data. Or you can also don't drop any of these. You keep all of the features and just introduce the regularizer here. We will come to that. We will explain it more later on. That's another option. And in fact, for the regularization, there are more than one option. Okay, we're gonna come to discuss them. Okay, and the benefit of every one of them. Okay, so anyways, now you look at the correlation. So let's look at which one are the most correlated. Okay, let's sort them. Here, what we are doing, we are actually sorted them by the correlation with respect to the target variable y. Okay, so let me look at this here. Okay, so of course y is very correlated to itself. That's not what we are looking for. The most correlated one is x1, then x5, then x6, then x2, and so on. So these are the, like, if I wanna look at the most the top three, these are 6x1.7. This is very correlated. 5.5 is correlated. 6.5 is correlated, and then after that, like most of the others, like this is okay, weakly correlated, but this is very low correlation. This one, and this one. We may drop this and build a model based on the other ones and see how that model performs. Okay. So here, this is how we compute the closed form solution. Okay, so x0 is equal all the input features. We are dropping the last column because the last column is our target variable y. Okay, and by the way, you can also, these numbers here, you can also look at like using the heat map. So here, when the color is very like close to, I don't know, white, is this, can we say white here? So then like the correlation is, it's very positive correlation, and the black is a very negative correlation, and in the middle, like it's here. Okay, for example, this is like like this represents like low correlation between this feature and that feature. Okay, back to this here. So here we are extracting all the columns, dropping the last one. These are our input features, x0. Okay, so the values of all those columns, all columns except the last one, because the last one is the target variable. This is the matrix of our input features. Okay, and y, the target variable, will be the last column. Okay, the values for the last column. And then x0 here, we don't have the feature of all ones at the beginning, so here we're doing that. Okay, we are concatenating a vector of all ones with our input features. So we are adding the ones so to account for beta 0. Okay, we can also do it this way, each stack, it's the same thing. Okay, so now we created x and y. Okay, simply we just use, like, this is nothing but the inverse of x transpose x times x transpose y, the optimal solution here, shown here, mathematically. We're computing that. That's it. So if we do that, we print it out. These are the optimal values for our model parameters. This is beta 0, beta 1, beta 2, and so on. Okay, we can also do it using the scikit-learn library. So we import linear regression. We create the object and we fit it in our data. Here we're not accounting for the intercept. Okay, so we're not appending the vector of all ones, because we already found it to be 0 here. Anyways, in general, you should do that, because in general, you're not computing. If you are computing it using this formula, then you don't need to call this function. So in general, I would say append all ones here. So like it will be more general. If the best choice is to set this to 0, it will be set to 0. Okay, and that's it. So we get the same values. Okay, so let's stop here for today. Okay, you can also run gradient descent actually. Okay, for the same problem, you can take that as a homework. Okay, you run gradient descent with like using this pseudocode, or you also can use the matrix and vector format. Okay, so with that, we stop here for today. Thanks for watching. See you next time, inshallah. Assalamu alaikum.